formerly VDR, now Claro VDR. There's a whole merger going on. But I'm also an electrical engineer from this very university and master's in engineering sciences. And the topic that I'll be discussing today is specifically my thesis dissertation. So this brings back some not so old memories. So I hope you enjoy them as much as I did. So the topic of today's presentation is channel modeling in IoT deployments supported by LEO nanosatellites. Right. So to kick things off, we'll begin. It's not working. Thank you. Okay. So to kick things off, we're just going to talk a bit about the motivation. So what's the topic that we're dealing with, right? There's a paradigm that's called IoT, Internet of Space Things, which extends the traditional IoT sort of framework to enable novel applications which are not normally supported in traditional IoT deployments. Some of these applications include fauna tracking, monitoring of hydric resources, communication in disaster scenarios, and among others. The key difference here is the fact that in many deployments, you don't have a terrestrial uplink, right? You need to establish a direct-to-satellite link. And what these scenarios have in common is the fact that you definitely need to have this flexibility. You can have like a base station that's connected to a fiber uplink, right? You need to be connected directly to the satellite. And this is the big advantage of this paradigm, right? So on screen, you can see this is a diagram of the IOSC architecture. Circled in blue is the segment in which we'll be focusing in, right? You have IoT devices on their surface, right? And you have satellites, which serve as uplink for these devices. So is there any way to hide the Zoom thingy? I'll just continue it. So what's the problem statement? What's exactly the topic that we're trying to address? So due to the nature of this scenario, there's significant signal degradation due to many sources, right? Physical phenomena mainly, right? And there are many models in literature that have been proposed to tackle this problem, but there's no consensus around which one is best suited for this scenario, right? So on screen, you can see a very simplified representation of the scenario that we're studying, right? So you have several devices, IoT devices in the Earth segment, each one establishing a direct satellite link with a nanosatellite, which is in low Earth orbit. And there are many details of this scenario that kind of add additional complexity to the channel modeling. For example, as you can clearly see, the elevation angle that each IoT device has with respect to the uplink is different, right? And this leads to different channel models for each device, right? I lost it again. Yeah, there we go. Thank you. So what's the hypothesis of this work? So we propose that a channel model that incorporates the Doppler effect, multipath, shadowing, and a high degree of time variance can accurately capture the physical link dynamic of the direct-to-satellite IoT scenario, right? And specifically the scenario in which we consider LEO nanosatellites in the space segment, right? So this is the hypothesis that we will try to prove and we will try to defend in this work, okay? So how do we begin studying this topic? So like I said, there are many models in literature. So first, we're going to just cover the basics of channel modeling in this environment, and then we will review the different models that are available. So we have identified three main physical effects that cause degradation that should be addressed as part of channel modeling. The first one is multipath, the Doppler effect, and then shadowing. Okay, so we will be covering each phenomena a bit in more detail. So first, multipath. This is commonly known as a short-scale fading phenomenon. This is mainly caused by interactions between the transmitted signal and different objects that are located in the environment. These objects act as scatterers, right? And what these scatterers cause is that in the receiver end, what you get instead of just the transmitted signal, you get a superposition of several copies with different attenuation coefficients, different phase delays, different time delays, and all that is added up into the receiver end, right? So you don't get like an ideal impulse response channel. You get a very complex channel, which is usually modeled as a sum of, like I said, copies of the transmitted signal with different coefficients, and this leads to distortion, of course. So on screen, you can see in figure 3 a very simplified diagram of how multipath can be modeled. We have n scatterers. Each scatterer creates its own path and leads to a different signal that's being added up into the receiver end. So in most scenarios, the complex expression that you just saw can be utilized to obtain an impulse response with the following structure. So there's a mu of t function, which multiplies direct delta. This, of course, reflects a time delay that's being caused by the channel. And in the previous equation, mu of t, the absolute value of mu of t follows a Rayleigh distribution. This, of course, considers that there's no line of sight. If you add line of sight, then you just replace mu of t with mu sub rho of t, which includes m of t, which is the direct component. And in that case, the module of that expression follows a Ricean distribution, right, which is just a Rayleigh with an upset component. Second phenomena, the Doppler effect. You're probably very familiar with the Doppler effect, at least at a fundamental level. So this is, of course, caused by a frequency shift when there's relative motion between transmitter and receiver. There's a very simple, formula that's usually used to kind of model the frequency shift that's caused. There's a very common diagram that you use to kind of illustrate when the Doppler effect occurs and how it works and all that. But when you talk about the Doppler effect in multipath environments, there's a bit of more complexity to be considered, right? You need to model the effects statistically. You usually use a power spectral density. There are two power spectral densities that are commonly used. One is the Jakes power spectral density and the Gaussian's power spectral density, equations 5 and 6. Depending on the scenario that you're studying, you tend to use one over the other. Usually, the Gaussian PSD is commonly associated with more frequency selective scenarios, right? So less of a flat channel response. Very similar as we did with multipath, you can usually separate the power spectral density of the diffuse component in two different elements, right? And like I said, depending on the setting, you can just tend to model the scenario better with a Gaussian or a Jakes PSD. The final physical effect that we will be considering is shadowing. Shadowing is usually considered a large scale fading phenomenon. This is caused by obstructions, large objects that are interposed between transmitter and receiver. This causes fluctuation in the received power. And since this is a phenomenon that's a bit unpredictable in real world settings, this is usually modeled statistically, right? This is meant to represent, for example, when you have a link between an Earth device and a satellite, and you have buildings that are interposed, or cars or buses, and that usually can be modeled statistically as opposed to kind of deterministically. This is a phenomenon that's been studied mostly empirically. This is a very big difference with respect to the two previous phenomena. The most common representation of shadowing is a log normal shadowing, which is this beautiful expression that you see in equation 8. It's a bit of complex and hard to handle, but this is the most commonly associated model with log normal shadowing. Now, the problem with having such a complex expression is the fact that when you have both shadowing and multipath present, the resulting distribution tends to be intractable, right? It's very hard to manipulate. You don't have an analytical expression for the distribution that you get, right? And this leads to all sorts of mathematical complexities when you're trying to manipulate expressions and get different results, right? What are the challenges of this specific scenario, right? We talked about phenomena in general that you should consider in channel modeling. Here we have identified at least 6 challenges that are specific to the IoT device supported by LEO nanosatellite scenario. So 2 big ones are power scarcity and limited power processing. You're talking about, in general, very small platforms, lean platforms. You don't have access to a ton of power. You don't have access to large processing power, both on the space segment as well as on the on the Earth segment. You're usually dealing with a very limited platform. Since you have a satellite that's in lower orbit, there's a very high delay. You're talking about distances of about 600 kilometers, so it's considerable. Not as prominent, for example, as geostationary orbits, but it's still very, very large, right? Another very important effect that's present in low Earth orbit is that you have very high tangential speeds, right? Satellites in low Earth orbit can travel at speeds of about 7 kilometers per second, if I recall correctly. And this causes a huge amount of Doppler effect, right? There's a ton of relative motion between the satellite and the Earth device. Additionally, due to the very dynamic nature of the scenario, the link parameters tend to be non-stationary, right? When you have multiple satellite passes over, a certain latitude of the Earth, usually the point in which, you have visibility is different every time. You have a different maximum elevation angle every time. You have a different window length. So it's all very dynamic and it's not at all stationary, right? And additionally, since you're usually dealing with IoT protocols, you tend to have very low bit rates, right? You don't tend to transmit like megabytes or gigabytes of information. You're usually talking about kilobytes, right? And since you're using very low bit rates, the channel is very dynamic. You usually tend to have a very short coherence time. What this means is that during the transmission of a single bit or a single symbol, rather, you can have several realizations of the channel process, right? So whilst you're transmitting a single symbol, the channel's already done all sorts of changes, and it's all unpredictable and very complex to model. Okay, so these are the kind of problems that we're trying to deal with when in channel modeling. What do we currently have in literature, right? So we have a ton of channel models, of course. We have just selected 6 here, which we believe that tend to represent this scenario very, very well. So the first model is probably the most rudimentary or simplistic model, which is Lu's model. This was intended originally for rural environments. It's a very simple model. It uses a Rayleigh distribution to model multipath, but normal distribution for shadowing. And it was intended for geostationary systems, right? Which, like we talked earlier, are very different from geosystems, right? Channel models start to evolve. You then get to the Lutz model. This has a very big difference. It is a 2-state model. It has a good and a bad state. This was devised with urban environments in mind, where you tend to have communications of uninterrupted, unobstructed windows of visibility, divided by large windows of obstructions, right? You have buildings, you have cars, you have all sorts of things. So in the good state, you have a Ricin distribution, which represents line of sight and not so hard shadowing, while in the bad state, you have Rayleigh log normal distribution, which of course reflects the absence of a line of sight component, as well as a heavier shadowing present. However, this was also designed for geosystems. The Arcturan model is a very unique sort of approach to channel modeling because it's constructed as a linear weighing of 3 different distributions, the Rice, the Rayleigh, and the Lu PDFs. So as this is constructed as a linear weighing, you have a ton of flexibility, and it also divides the elevation angle in 5-degree increments, right? So what you get is that you get different set of components at 5-degree increments of the elevation angle. And since in LEO orbits, you can sort of predict the trajectory that a satellite will follow, you can usually write the angle as an expression of time, right? So this channel model has the inherent property of being able to be dynamic, right? Like right out of the box. So this is a big advantage with respect to the 2 previous models. Wang's model is part of a family of models that are built as extensions of Lu's model. It has a big difference. It considers independent shadowing for both the line of sight and the multipath components. Both are modeled as log normal, but with their independent variables with different components, different parameters. And a Ricin distribution is considered all multipath. This model has been tested in LEO and medium Earth orbit settings, so this is a big advantage as well. Petzold's model, again, part of the family of Lu sort of related models. It has a big difference that it includes the Doppler shift explicitly in the line of sight component. And additionally, it also allows the in-phase and quadrature components of the multipath portion of the signal to be correlated. And this is more in line with real-world empirical data. Finally, we skip 22 or so years into the future and we get to the FSM-CTS model. This is a very novel approach to channel modeling, which is, as its name suggests, based on finite state Markov chains. It models both multipath and the Doppler effect. It doesn't include shadowing. It's going to be a big point further down the presentation. The key idea is dividing the communication window in 2 sectors, the good and the bad sector, depending on the elevation angle. And this is a model that was designed specifically for low Earth orbit systems. So this probably a very big advantage with respect to the other models. So we have a bunch of channel models that can be used to model this scenario. We have no way to evaluate them, right? We have no way to compare them, no way to determine which one might be better for this scenario. So this chapter 3 is the first of 2 contributions that this work has, to the community, so to speak. Here we will be presenting a framework that we're proposing to evaluate models and compare them and sort of analyze and lead and to try to get to a definitive answer, right? So this is a very simple 3-step methodology that we're proposing. Step 1 consists of a weighted score assessment. So we construct a metric based on 3 criteria. We assign weights to each criteria and we evaluate each model against that criteria. We get a number, which is the weighted score, and we use that to rank the channel models. Step 2, we take a subset of set models and we run them through simulations to compare performance, right? Get an idea of how each model would perform in different scenarios. And finally, step 3 consists of a validation in a in-the-loop scenario, right? This is meant to sort of test each model in a more real-world setting, right? With real hardware and, sort of to get an idea of how these models would perform in the real platforms, right? Fortunately, due to time constraints, step 3 is left for future work. However, it is considered part of the framework that we're proposing, right? So we won't be seeing results for step 3. Step 1, weighted score analysis. So as I mentioned previously, there's 3 criteria, Cs 1 through 3. The first one aims to measure how well the model represents physical phenomena, multipath, the Doppler effect, and shadowing. Higher number means better representation. The second coefficient is meant to evaluate how dynamic each model is. So how well the time variant nature of the problem is being captured in the model. And the third criteria is the computational complexity, which measures how reliant the model is on processing power. Why are we considering C3 to be part of the evaluation? Because we need to remember that we're working with very limited platforms, right? We could be having very deterministic, highly complex models that run ton of simulations or whatever to model the problem, but we don't have that kind of horsepower in the platforms, right? So we're choosing, as we're doing a weighted score metric, we're choosing 3 coefficients, W1, 2, and 3. We're considering W1 and 2 to be equal to 2 and W3 to be equal to 1, because even though we believe that computational complexity is relevant, it is mostly relevant when you're talking about higher layer applications, right? When you want to use the feedback from the physical layer in the link layer or the network layer or whatever, right? That's when you sort of need to have access to the channel model for simulations and all that good stuff, right? So after running each model with the criteria, we get the following metrics that you see on the rightmost column, right? So since we discussed previously, each model tends to sort of leave out a single phenomena, or for example, has a very simple representation of multipath and shadowing, such as the case with the Liu and Lutz model. Patzel's model has a very complete representation of both multipath, Doppler, and shadowing. This leads to the results in column C1. When you talk about the degree of time variance, you usually have very static models. The big sort of outliers here are, of course, the Actura, the Patzel, and the FSM-CTS model, which have a certain way to include time variance. So this leads to the scores in column 2. And in general, you don't have very complex models, with the only exception being the FSM-CTS model, right, which leads to the lowest score in column 3. When you run this through the weighted score metric, you get column WS, right? And we have decided to shortlist the 3 candidates that you see highlighted in green. And we have added a final sort of theoretical column, right? Which poses the question, what if we had a model that was like the FSM-CTS model, but did include shadowing, which is its only sort of shortcoming in the C1 criteria, right? So we'll leave that as a sort of what if, but this will be relevant in the next chapter, right? So we have a set of models. We have shortlisted. So we have the Actura, Patzel, and CTS. We intend to run them through simulations, right? These are the parameters used. You might be wondering why is Liu's model included and why is Patzel's model not included? So unfortunately, due to time constraints as well, we weren't able to model Patzel's model for simulation. And we have included loose model only as a reference, right? Loose model, being such a traditional approach to channel modeling, is usually considered a baseline approach to satellite channel modeling. So we're including it just as reference. So just a refresher of the topology. And we are considering two scenarios for simulation. One scenario at elevation angle equal to 0, which would be reflecting the bad state, and at an elevation angle of 20, which is the transition to the good state, right? So we have a bad state and a good state simulation. This is mostly just an exploratory simulation. So here we are using 10 to the 4 samples, and we're plotting the mean fading amplitude of each model simulation, right? So you can see that the LU and the Improvement model tend to have a very similar stochastic behavior. You have a lot of variance. The amplitude of the variance is very similar. You can see clearly the two different elevation angles that are being simulated. And the key difference here is the FSM-CTS model, right? This model tends to clearly have a different stochastic behavior, right? There's more of a trajectory. There's not a lot of wild variations from low amplitude to high amplitude, and this is a very significant difference. It kind of sets it apart from other models, right? Again, remember that loose model is only included as a reference. And in a similar vein, here we have plotted the CDF of the fading amplitude for a wide spectrum of models. The key elements here are the simulated Acturan, LU, and the FSM-CTS models, right? So which are the thick, that's like a magenta, right? Thick magenta, dashed black line, and a dashed dot cyan line. I don't know if you can see that very well, but basically what we're trying to get here is that with the right set of parameters, you can have very similar behaviors, right? So there is a set of parameters that you can choose for the simulation that leads to probably a fair ground for comparison. A key behavior that's illustrated here is the fact that Acturan's model, since it's built as a linear weighing of three distributions, can interpolate between the three distributions, right? You can see that with different sets of Acturan parameters, you can kind of move through the spectrum of Rayleigh, LU, and Rice distributions, right? This is a very interesting behavior and highlights the flexibility that this model presents, right? So we have performed various simulations that are mostly exploratory in this stage, but this kind of leads to a certain idea of how these models would be performing under more realistic settings. Of course, the next step would be to include Patzel's models in the simulation and then move on to the final step of the process, which would be simulation and hardware in the loop settings, using metrics such as, for example, bit error rate to measure how well we are representing real-world data. But like I mentioned previously, unfortunately, step 3 is not included as part of the scope of this work, right? So this was the first contribution. Then the second contribution, which we have been kind of hinting at throughout the presentation, we're presenting an enhancement to one of the models that was previously presented, right? We're going to just do a very quick review of the FSM-CTS model, just to kind of understand what we're improving. So we already said that this is designed for LEO scenarios. We're dividing the communication window in 2 sectors. You can see this clearly in figure 10. Thank you. This figure, you can clearly see that lower elevation angles have harsher fading phenomena, right? You have large scale fading, small scale fading, and when you get to higher elevation angles, such as here, you have line of sight components. You don't have shadowing anymore. You have better channel conditions, right? So this is the behavior that's being illustrated in figure 10. So what this model includes, it includes multipath, the Doppler effect, and elements of the LEO geometry, right? We just talked about shadowing, right? But it's not present in the mathematical modeling of the channel, despite being one of the key phenomena in LEO satellite communications, right? So this is the kind of the only glaring sort of thing that's missing from this model, and this we'll be trying to address. So how does this model work? So each sector, so the G and the B sector, is represented by its own k-state finite state Markov chain. It's illustrated here in figure 11. So this is the chain representing the G sector. This represents the B sector, right? What are the components of this Markov chain? Each state is a different BSC, or binary symmetric channel, right? This BSC is constructed by equipartitioning each sector's PDF. So the G sector is modeled with an Akagami PDF. This models line of sight, multipath, and the Doppler effect. And the B sector is modeled with Rayleigh distribution, right, which models the absence of a line of sight, so there's no line of sight present, partial multipath, and Doppler effects. There's no shadowing present. Okay. So you get the PDFs of each sector, and then you get this set of equations 10 to 15 that allow you to construct the parameters that would be used to simulate the Markov chain, right? I'll only mention one sort of important characteristic of equation 15. This thing right here is solved using series-based approach, and this is a big key difference that this model uses very cleverly, right? So this integral that you see right there that could be very tough to solve numerically or analytically, through a series-based approach, you can get a very elegant result that it's very accurate, right? So what's the improvement? We basically intend to address a very relevant limitation of the model, just lack of shadowing. How will we accomplish this? We will attempt to replace the Rayleigh PDF with a new distribution that allows multipath, Doppler effect, and shadowing to be represented as part of the physical phenomena in the channel. We will be referring to the new channel model as the enhanced FSM-CTS channel model. This is a simple methodology that we'll be using. We need to select the distribution, we need to implement the FSMC, and then we will evaluate through simulation. Okay? Step one, what distribution shall we use? So a very natural solution would be to add a log normal distribution to the B sector, right? We already saw that log normal is the most common distribution used for shadowing. However, you can't kind of do that so easily, right? Since the distribution that you get is immediately intractable. And any other calculation that you try to do with this distribution can only be done numerically, right? So that's kind of out of the window. However, there are several alternatives to the Rayleigh log normal distribution, right? Substitutes that you can use. The K distribution is one of them. What's the K distribution? It's just a composition of a Rayleigh and a gamma distribution. That's a PDF shown in equation 17. This distribution provides a good estimate of the Rayleigh log normal distribution while having a much simpler mathematical treatment, right? And of course, we have the advantage. It's a good starting point, right? There's already an implementation of an FSMC using K distribution in reference 18. So this is a very good starting point. So we use basic relationships between the fading amplitude, instantaneous SNR, to deduce equations 18 and 19, the PDF and CDF of a K distribution. We arrive at the model parameters, which are beta and the normalized SNR, SNR per symbol. There's another parameter, which is alpha, related to the mean signal power, but since we will be assuming the mean power to be 1, we should leave that parameter as 1/2, since you can demonstrate that that's the relationship between alpha and gamma. So alpha will be half unless stated otherwise. So we have two degrees of freedom here. We have beta and we have the SNR per symbol. So using the distributions, you compute all the equations again. Some you can solve analytically, mainly 1 through 24, I believe. But 20 and 25, you kind of have to do numerically. There's kind of no way around that, right? Using those parameters, you can start to solve things analytically. For example, you can get the level crossing rate. In equation 26, we have two auxiliary variables just to simplify notation, but you can get the level crossing rate analytically. And then you can employ simulations, right? What simulations are we using? We're using Monte Carlo to obtain an estimation of this model's bit error rate. We're transmitting a total of 10 to the 6 bits, running 400 iterations of Monte Carlo, and we're estimating the BER empirically and comparing it, we're simulating the bit error rate and we're comparing it with a theoretical value, which is represented in equation 29, which is an analytical closed expression. So U is just a function that is well known. It's the Tricomi function. Parameter set used for the simulation. We're employing 4 different values of beta. We're considering SNR from -10 to 30, which is a step of 5 dB. We're working with a carrier of 2.4. This is mainly because that's what is used in literature, in the FSM-CTS work specifically. And we're considering elevation angle maximum of 90 degrees, right? So we're considering a window in which you can have a whole range of elevation angles. Results. So here we have the results of the Monte Carlo simulations. All the lines are analytical results. All the dots or family of this dots, right, like circles, asterisks, crosses, and plus signs, are simulated results. We're using 5 dB increments. And you can see that especially at higher SNR values, you can get a very good representation of the analytical expression, right? So the FSMC model behaves very similar to the analytical model at high SNR values. This is very good. This is what we want, right? However, as you approach lower SNR values, as you can see here, the values start to get a bit off, right? That's when the estimate starts to fall off a bit, right? You don't get a very close representation of the analytical channel, right? Another very interesting behavior that you can see here is the fact that when beta, which is a parameter which models the degree of shadowing, as beta increases, you start approaching more and more towards the Rayleigh distribution, which is the blue line, right? This is because higher beta means less shadowing, means that you're getting closer and closer to the pure Rayleigh scenario. This is consistent with what is found in literature, so this is very good. And of course, as beta approaches -1, which is the minimum, the sort of the BR curve starts getting more and more lifted, like start to get to the pure 0.5 purely noisy channel, right? And this is, of course, again, consistent to what's found in literature. So here we just talk a bit about what I just said, a bit of conclusion that you get out of the analysis. And we have a clear problem, right? The results are very good, high SNRs, that's good. But we have a very big discrepancy at low SNR values. And we have no conclusive evidence yet, but we believe that this is due to the numerical integration that's used to calculate the input error rate, right? Remember that I said that the CTS model uses a series-based approach? That's a big advantage that that model has, right? It doesn't use numerical integration. We believe that this might be the cause of some of the discrepancies, right? So, I'm a bit over, I'm sorry, but I'm just wrapping up. So conclusions. So what have we accomplished? We presented a generalizable methodology for channel model analysis and the Leo-based directed satellite IoT. We have good initial results. Nothing conclusive yet, but we have, we're on the right track at least. We have listed three models, Accurance, Petzels, and the CTS model for further evaluation. We presented some exploratory preliminary simulation results for two of the shortlisted models. Petzels model is still pending. And we managed to improve an existing channel model, right? We presented the enhanced FSM-CTS model, which includes shadowing, addressing one of the only maybe sort of lacking points in the FSM-CTS channel. This model is a good fit at high SNR values. There's a big discrepancy at low SNR values, which needs to be further looked into, right? And of course, this naturally leads to future work, which are all along the lines of what we just said, right? We need to finish using the framework for channel model comparison, do the simulations that we're missing, get with the hardware in the loop stage to kind of evaluate in a more realistic setting. And with respect to the new channel model proposed, we need to study this behavior at low SNR symbols. Other avenues for improvement could be to analyze the end-to-end system, right? We only talked about the B sector. We need to remember that this is a two-sector problem, right? So maybe a good idea might be to study the whole system, end-to-end, right? Additionally, there are other alternatives to the K distribution. Here I've named like 5. You can use different distributions to kind of substitute radial log normal. And of course, there's a paper that came out, I believe, maybe it's finished. Right, like I wrote the last dot on my piece, and this paper came out like the day after. And this is a very big improvement with the original channel model, right, which is a multi-sector theory. So you're not only partitioning in 2 windows, you get like degrees, and that's where it's better, and you might want to extend this analysis to that as well. So I'm sorry I'm a bit over. I'd like to thank you for your attention, and of course, any questions, comments are welcome. Thank you very much.